Implementation of Polaris Spaceplanes Hypersonic Transport Technology by 2026. Introduction. In the rapidly evolving field of aerospace technology, Polaris Spaceplanes, a German startup founded in 2019, is making significant strides with its hypersonic transport technology known as Aurora. With a recent contract from the Federal Office of Bundeswehr Equipment Information Technology and In-Service Support (BAINBW), Polaris has secured a budget allocation of €12 million for research and development R&D and testing, aiming for the project's completion by 2026. This report outlines the critical development phases of the Aurora project, the strategic importance of hypersonic technology, and the implications for the aerospace and defense sectors. Background. Polaris Spaceplanes emerged as a spin-off from the German Aerospace Center (DLR) and has quickly established its vision to develop a multipurpose hypersonic spaceplane. The Aurora project is designed to function as both a research vehicle and a platform for defense applications, including rapid satellite deployment. The project aligns with Germany's broader defense strategy, emphasizing the need for advanced capabilities in response to changing geopolitical landscapes. Development phases. The development of the Aurora hypersonic transport technology is structured into 4 critical phases. Phase 1: Design and initial development. The initial phase focuses on the design of a fully reusable hypersonic research vehicle. This vehicle will serve multiple purposes, acting as a testbed for hypersonic flight and facilitating scientific research and defense-related applications. The design phase is crucial as it lays the groundwork for future manufacturing and flight testing. Key objectives include: design specifications, establishing aerodynamic profiles, structural integrity, and propulsion systems. Reusable framework, ensuring that the vehicle can be reused multiple times, significantly reducing operational costs compared to traditional rocket systems. Phase 2: Construction of demonstrators. Following the design phase, Polaris will leverage its experience from previous smaller demonstrators, Mira 2 and Mira 3. Each of these 5-meter-long vehicles has undergone over 100 successful test flights testing various technologies including aerospike rocket engines. Significant milestones during this phase include: development of Mira demonstrators. These vehicles have served as platforms to test aerospike propulsion and other technologies essential for hypersonic flight. Engine testing. The successful in-flight ignition of the AS-1 linear aerospike engine marked a pivotal achievement, proving the viability of this advanced propulsion system. Phase 3: Full-scale development of Aurora. In this phase, Polaris will transition from demonstrators to a full-scale hypersonic spaceplane approximately 28 meters long. The Aurora spaceplane is designed to achieve speeds exceeding Mach 5/6. 125 km per hour and can carry payloads of up to 1 ton into low Earth orbit. Key aspects of this phase include: integration of technologies, combining jet engine capabilities for takeoff and landing with rocket propulsion for hypersonic speeds. Payload versatility. The ability to carry small satellites and other payloads enhances the vehicle's utility for both commercial and defense purposes. Phase 4: Testing and operational readiness. The final phase involves rigorous flight tests to validate the vehicle's capabilities in hypersonic transport and satellite deployment. This phase is crucial for ensuring that Aurora meets both military and commercial specifications. Objectives include: flight test program, conducting a series of controlled flight tests to demonstrate performance and safety. Operational readiness assessment, evaluating the vehicle's readiness for deployment in real-world scenarios, including potential military applications. Budget and funding. The €12 million budget allocated by the German government highlights the strategic importance of hypersonic technology in enhancing national defense and space access capabilities. This funding reflects a broader trend in Europe where increased defense spending is prioritized in light of evolving geopolitical challenges. The budget allocation will cover Research and development costs, funding for engineering design and prototype development. Testing and validation, resources for conducting extensive flight tests and operational assessments. Key developments timeline. 2019, establishment of Polaris Spaceplanes as a DLR spin-off. April 2023, award of a contract for the development of the AS-1 linear aerospike rocket engine. October 2024, successful in-flight ignition of the AS-1 engine aboard the Mira-2 demonstrator. February 2025, BAINBW contract awarded for the design of the Aurora hypersonic research vehicle, marking the initiation of the next development phase. Common points across sources. Multiple sources share a consensus regarding Polaris's focus on developing a reusable hypersonic vehicle that integrates both aircraft and rocket capabilities. They highlight the significance of aerospike engine technology, which is viewed as a breakthrough in high-speed propulsion. The emphasis on dual-use applications for defense and scientific research is also universally acknowledged. Differences in perspectives. While some sources concentrate on the technical achievements and capabilities of the Mira demonstrators, others emphasize the strategic military implications of the Aurora project. There is also variation in the depth of technical detail provided about the aerospike engine and its historical context, reflecting the diverse interests and expertise of the reporting outlets. Some highlight the historical challenges faced in the aerospace industry regarding aerospike technology, while others focus on the potential for innovation through advanced cooling techniques and materials. Conclusion. Polaris Spaceplanes is poised to significantly impact both the aerospace and defense sectors with its innovative hypersonic transport technology. The Aurora project represents a critical development in enhancing Europe's space capabilities and national defense strategy. With a clear timeline and a substantial budget allocated for its successful implementation by 2026, Polaris is set to redefine the boundaries of hypersonic flight and space access. As the project progresses through its development phases, it will be essential to monitor milestones and achievements that will ultimately determine the success of this ambitious endeavor. The implementation of the Polaris Spaceplanes hypersonic transport technology by 2026 involves several phases that have been outlined in the project. However, there are some counterintuitive aspects to consider regarding the technology, its funding, and the implications of its development. 1. Budget allocation versus project scope. The €12 million budget allocated for the development of the Aurora spaceplane may seem substantial at first glance, especially for a hypersonic vehicle. However, in the context of aerospace development, this amount is relatively modest. Traditional aerospace projects often require budgets in the hundreds of millions or even billions of euros. The expectation that a fully reusable hypersonic vehicle can be realized within this budget raises questions about the feasibility of achieving the ambitious goals set for the project, especially regarding the extensive R&D and testing needed. 2. Technological leap versus incremental development. While Polaris has made significant strides with smaller demonstrators, the leap from a series of successful tests with 5-meter vehicles to a full-scale 28-meter hypersonic transport is a considerable jump. This suggests that while the incremental development path has produced promising results, scaling up to a functional hypersonic vehicle introduces complexities that may not have been fully addressed in earlier phases. The notion that past successes with small vehicles will directly translate to larger, more complex systems is often misleading in aerospace engineering. 3. Reusable technology in a defense context. The emphasis on creating a reusable hypersonic vehicle typically aligns with commercial aerospace goals, where cost efficiency through reusability is paramount. However, in a defense context, the need for such a vehicle raises counterintuitive questions about the military's operational requirements. Military operations often prioritize reliability and performance over cost, which may lead to a preference for expendable systems that can be deployed without the complexities associated with reusability. This dichotomy could challenge the market acceptance of Polaris's Aurora in defense applications. 4. Historical context of aerospike engines. The project leverages aerospike engine technology, which has been in the conceptual phase since the 1960s but has faced numerous engineering challenges that have prevented its widespread adoption. The assumption that new advancements in cooling technologies and materials will easily overcome these historical hurdles is optimistic. Historically, many aerospace innovations have encountered unanticipated technical difficulties during development, leading to delays and increased costs. 5. Strategic military implications versus commercial viability. The dual purpose of the Aurora as both a military and commercial vehicle contrasts sharply with typical market dynamics. While the military may seek cutting-edge technology for national defense, the commercial market prioritizes cost-effectiveness and reliability. The expectation that a vehicle developed primarily for military applications can seamlessly transition into the commercial sector raises questions about its market viability, particularly regarding payload capacity and operational costs. 6. Geopolitical influences on funding and development. The decision to allocate funding towards hypersonic technology appears to be influenced by shifting geopolitical landscapes and the need for enhanced defense capabilities in Europe. However, the assumption that increased spending will automatically lead to successful technological advancements can be misleading. Budget increases do not guarantee successful outcomes, especially in high-tech fields where innovation often comes with high risk and uncertainty. 7. Public perception and acceptance. The general public often views advancements in aerospace technology with optimism, expecting rapid progress and successful outcomes. However, the reality of aerospace development is fraught with challenges, including regulatory hurdles, safety concerns, and public acceptance of new technologies. The assumption that the public will readily embrace hypersonic transport technology ignores these complexities and the potential for backlash against perceived military applications. In summary, while the Polaris Spaceplanes project embodies a vision of advanced hypersonic transport technology, the realities of budget constraints, technological challenges, and market dynamics introduce counterintuitive considerations that could impact the project's success and acceptance in both military and commercial arenas. The report on Polaris Spaceplanes' implementation of hypersonic transport technology in the form of the Aurora spaceplane contains several critical elements that are significant but often overlooked by the general audience. The following points highlight the important content within the report, providing insight into why these aspects deserve greater attention. 1. Significance of the aerospike engine technology. While the report mentions the aerospike engine's role in the development of the Aurora, many readers might underestimate its importance. The aerospike engine, particularly the AS-1 engine developed by Polaris, represents a potential paradigm shift in propulsion technology. Unlike traditional rocket engines, which struggle with efficiency at varying altitudes, aerospike engines maintain optimal performance across a broader range of conditions. This is due to their unique design, which allows them to adjust to changes in atmospheric pressure, enhancing thrust and fuel efficiency. The successful in-flight ignition of the AS-1 engine in October 2024 is a notable milestone. It not only showcases Polaris's engineering capabilities but also signifies a historical achievement, as aerospike engines have faced challenges that previously hindered their adoption in mainstream aerospace applications. If Polaris can overcome these historical challenges, it could lead to widespread adoption of aerospike technology, revolutionizing both hypersonic travel and space access. 2. Dual-use applications of Aurora. Another critical aspect that might be overlooked is the dual-use nature of the Aurora spaceplane. The report emphasizes that the vehicle is not solely designed for civilian applications but also has significant military and defense implications. By serving as a testbed for hypersonic flight and a platform for defense-related applications, Aurora could enhance national security and military capabilities. The potential for Aurora to function as a small satellite launch system adds another layer of significance. As the demand for low-cost satellite deployment increases, Aurora's ability to deliver payloads into low Earth orbit could position Germany and its allies as leaders in the rapidly evolving space economy. This dual-use capability aligns with broader trends in defense and space policy, where technological advancements are increasingly viewed through the lens of national security. 3. Strategic importance of European defense spending. The report also touches upon the broader context of increased defense spending in Europe, particularly in light of changing geopolitical landscapes. This is a point that many may overlook as they focus solely on the technological aspects of the project. The €12 million budget allocated by the German government for Polaris is indicative of a strategic pivot in defense policy responding to rising tensions in global geopolitics. This funding not only supports the development of hypersonic technology but also reflects a growing recognition of the need for advanced capabilities in the face of potential threats, as Europe seeks to bolster its defense posture. Investments in technologies like those developed by Polaris could play a crucial role in ensuring regional security and maintaining strategic autonomy. 4. Timeline and momentum of development. The timeline provided in the report outlines significant milestones from the company's establishment in 2019 to the anticipated completion of the Aurora by 2026. However, the rapid pace of development and the ambitious timeline may be underappreciated by those outside the aerospace sector. The fact that Polaris has progressed from conceptual design to successful test flights within a relatively short timeframe speaks to the company's engineering expertise and the effectiveness of its R&D efforts. The historical context of previous efforts in hypersonic technology, particularly in Europe, suggests that Polaris's momentum could inspire further innovation and investment in the aerospace sector. The successful execution of its development phases could set a precedent for future projects, paving the way for new entrants into the spaceplane domain. 5. Commercial viability and market implications. Finally, the potential commercial viability of Aurora as a cost-effective means of accessing space is a significant point that may not receive adequate attention. The ability to take off and land from conventional runways coupled with reusable design features positions Aurora as a potentially disruptive technology in the launch services market. The aerospace industry is increasingly looking for ways to reduce the costs associated with satellite launches and other space missions. If Aurora can achieve its design goals, it could provide a more affordable alternative to traditional rockets, thereby expanding access to space for both governmental and commercial entities. This could lead to a surge in satellite deployments and other space-related activities, significantly impacting the global space economy. Conclusion. In summary, the implementation of Polaris Spaceplanes' hypersonic transport technology through the Aurora project encompasses a wide array of critical developments that extend beyond the surface of technological innovation. The significance of aerospike engine technology, the dual-use capabilities of the spaceplane, the strategic context of defense spending, the ambitious development timeline, and the commercial implications all contribute to a complex narrative that deserves closer scrutiny. Understanding these aspects can provide a more comprehensive view of how Polaris's endeavors could reshape not only the aerospace sector but also broader geopolitical and economic landscapes. 1. Multi-purpose design and strategic importance. Polaris Spaceplanes is focusing on designing the Aurora hypersonic transport system as a multi-purpose vehicle that serves both scientific and military applications. This dual utility not only enhances the vehicle's value but also reflects broader strategic imperatives in Europe regarding defense capabilities and space access. The emphasis on a fully reusable design which can function as both an aircraft and a rocket aligns with the current trends in aerospace towards sustainability and cost-effectiveness. The budget allocation of €12 million signifies the German government's commitment to advancing national defense and space technology, particularly in response to evolving geopolitical dynamics. 2. Technological innovations, aerospike engine development. A critical aspect of the Aurora project is the development of the AS-1 linear aerospike engine, which represents a significant technological innovation in propulsion systems. The successful in-flight ignition of this engine during tests with the Mira demonstrators marks a milestone in hypersonic flight technology. Aerospike engines offer advantages in efficiency across varying altitudes compared to traditional rocket engines. However, their historical challenges, such as cooling and manufacturing complexities, have hindered their adoption. Polaris's focus on overcoming these challenges could pave the way for more efficient hypersonic vehicles and redefine propulsion technology in aerospace. 3. Development phases and timeline. The structured four-phase development plan for Aurora is crucial for managing the complexity of hypersonic flight technology. Each phase is designed with specific objectives, from initial design and demonstrator construction to full-scale development and operational testing. The clear timeline leading up to 2026 ensures that milestones are met and allows for iterative improvements based on testing outcomes. The successful progression through these phases will not only validate the technology but also build confidence among stakeholders in both the military and commercial sectors regarding the capabilities of hypersonic transport systems. 4. Implications for European defense and space strategy. The Aurora project is indicative of a larger movement within Europe towards enhancing defense capabilities and investing in advanced aerospace technologies. In light of increasing defense budgets and calls for a more robust European military presence, Polaris's developments could significantly contribute to the strategic landscape, providing rapid deployment capabilities and access to low Earth orbit for satellite launches. This aligns with the broader European goals for greater self-sufficiency in defense and space exploration, especially in a context where reliance on traditional power structures is being reconsidered. The interplay between technological advancement and defense strategy will be a focal point for discussion as Europe navigates its future in global security and space endeavors. 1. The Space Shuttle Program 1972 to 2011. NASA's Space Shuttle program is one of the most significant historical cases related to hypersonic transport technology and reusable spacecraft. The shuttle was designed to transport astronauts and cargo to and from low Earth orbit, and it operated for 30 years with 135 missions. The program was characterized by its development phases including design, construction, and extensive testing. Similar to Polaris Spaceplanes' Aurora project, the budget for the program exceeded $200 billion, and it played a crucial role in the construction of the International Space Station and the deployment of numerous satellites. 2. Boeing X-43 2001 to 2004. The X-43 was an experimental unmanned hypersonic aircraft developed by NASA as part of a research initiative to explore air-breathing hypersonic flight. It achieved speeds of over Mach 9.6, making it the fastest aircraft ever. The X-43's development involved multiple phases including design, construction, and rigorous testing, echoing the structured approach seen in the Polaris project. The X-43's success provided valuable insights into hypersonic flight technologies, influencing future projects in both military and civilian applications. 3. Lockheed Martin State Route 71 Blackbird 1966 to 1998. The State Route 71 was a long-range advanced strategic reconnaissance aircraft that was capable of flying at speeds exceeding Mach 3. It was designed during the Cold War as a response to emerging threats and played a vital role in intelligence-gathering missions. The development and operational history of the State Route 71 involved extensive research and budget allocations similar to those for the Polaris hypersonic spaceplane. Its unique design and advanced technologies, including the use of composite materials for thermal protection, have influenced subsequent aerospace designs and hypersonic research initiatives. Future outlook: implementation of Polaris Spaceplanes hypersonic transport technology by 2026. The development of Polaris Spaceplanes' Aurora hypersonic transport technology is positioned to revolutionize aerospace and defense sectors by 2026. This innovative initiative, backed by a €12 million investment from the German government, is set to unfold through 4 critical phases, each with specific milestones and implications for various industries. Below are predictions and insights regarding the future implications of this project. 1. Phase 1, Design and Initial Development 2025 to 2026. The initial design and development phase will focus on creating a fully reusable hypersonic research vehicle. By the end of this phase, we anticipate completion of the Aurora design. The final design will incorporate advanced aerodynamics materials and propulsion systems, leading to a prototype that aligns with both military and scientific applications. Regulatory framework development. As hypersonic technology evolves, there will be a need for updated regulatory frameworks addressing airspace management and safety standards for hypersonic flights. This could set a precedent for international regulations on hypersonic travel. 2. Phase 2, Construction of Demonstrators 2026 to 2027. The construction of full-scale demonstrators building upon the success of Mira 2 and Mira 3 will be a pivotal step. Key predictions include test flight innovations. The successful transition from small-scale demonstrators to larger prototypes will enable more sophisticated testing. We can expect to see breakthroughs in aerospike engine technology, which could lead to more efficient fuel usage and higher performance metrics. Increased partnerships. As Polaris progresses, collaborations with other aerospace entities and defense contractors will likely expand, fostering innovation and sharing of best practices in hypersonic technology. 3. Phase 3, Full-scale development of Aurora 2027 to 2028. The full-scale Aurora spaceplane, designed for hypersonic speeds exceeding Mach 5, will be a game-changer in multiple domains. Military applications. The Aurora could redefine military logistics and rapid response capabilities. Its ability to deliver payloads to low Earth orbit or conduct reconnaissance missions at unprecedented speeds will enhance national security. Commercial opportunities. The commercial implications of Aurora are significant. Potential applications in rapid cargo transport and passenger flights could emerge, tapping into a lucrative market for hypersonic travel that remains largely unexplored. By the end of this phase, we could witness the establishment of commercial partnerships aimed at developing hypersonic travel routes. 4. Phase 4, Testing and Operational Readiness 2028 to 2029. The rigorous testing and validation phase will focus on confirming Aurora's capabilities. Important predictions for this phase include operational readiness. By 2029, Aurora may be operationally ready for both defense and commercial missions. This readiness will mark a critical leap in aerospace technology, potentially leading to its adoption in various sectors. Impact on global defense strategies. The successful deployment of hypersonic technologies will likely prompt a re-evaluation of global defense strategies, with nations investing in similar technologies to maintain competitive advantages. This could lead to an arms race in hypersonic capabilities and a shift in military tactics. Broader implications and trends. 1. Geopolitical dynamics. As hypersonic technology matures, its influence on international relations will grow. Nations may adjust their defense postures and alliances based on perceived threats or opportunities presented by advancements in hypersonic capabilities. 2. Environmental considerations. The environmental impact of hypersonic travel will come under scrutiny. Efforts to develop sustainable propulsion technologies will be crucial, especially as public awareness of climate change increases. Innovations in materials and fuel efficiency will play a vital role in addressing these concerns. 3. Public perception and acceptance. The success of hypersonic travel will depend on public perception. Safety, reliability, and environmental sustainability will be key factors in gaining public acceptance for hypersonic commercial flights. 4. Investment in R&D. The €12 million allocation for R&D is just the beginning. We can expect further investments from both the public and private sectors as the potential for hypersonic technology becomes more apparent. This will likely stimulate job creation in aerospace engineering, materials science, and related fields. 5. Technological spin-offs. The technologies developed for Aurora may lead to innovations in other areas such as satellite deployment, space exploration, and even urban air mobility. The cross-pollination of ideas between different sectors will enhance the overall technological landscape. Conclusion. The implementation of Polaris Spaceplanes' hypersonic transport technology by 2026 promises to reshape the aerospace and defense industries significantly. With a clear roadmap and substantial funding, the project is poised to deliver groundbreaking advancements in transportation and military capabilities. As each phase unfolds, the ripple effects will be felt across various sectors, influencing geopolitical dynamics, commercial opportunities, and technological innovations, ultimately ushering in a new era of hypersonic travel.